The next thing we want to look at is how charged particles that are moving through magnetic fields react. And the answer is they get a force exerted on them. So whether you have a stream of charged particles coming from the sun or you have a current of electrons flowing down a wire, if those charged particles move through a magnetic field, that magnetic field is going to exert a force on them. So here we see a picture of a beam of electrons, and that beam of electrons is shot towards this horseshoe magnet, and we've already seen that in between the north and south poles of the horseshoe magnet there's going to be a magnetic field. And so when those charged particles, those electrons, which as you know have a negative charge, go through that magnetic field right here, they experience a force and get deflected. So notice out here where there's no magnet, the beam of electrons, those electrons are just shooting out straight. But once they interact with that magnetic field in that region of space where there's a magnetic field, that magnetic field exerts a force on them and deflects them. Now once they pass through the magnet, they're going straight again, but in the region where the magnetic field is, they get a force. It's deflected. Now, you can note a couple of things here. There's a picture right here which may be a little confusing. I want to try to explain it. We know that the magnetic field line is going north to south. And we know that the beam is going in this direction. So you can see here this blue arrow is showing the direction of the beam. And this blue arrow is showing the direction of the magnetic field. And what they're actually trying to show is that these guys are at a right angle to one another. It's kind of hard to draw that in 3 dimensions, but this is the basic idea, that the beam of electrons in this case is perpendicular to the magnetic field. But what's also perpendicular is the force. The magnetic field and the beam of charged particles, in this case the beam of electrons, they form a plane, and the force is perpendicular to that plane. So the force is always perpendicular to both the beam of charged particles and to the direction of the magnetic field. Now, I'm sure you probably learned in grade school that the Earth itself has a magnetic field. In fact, it acts almost like a giant bar magnet. And the reason you should know that the Earth has a magnetic field is because that's how compasses work. The compass needles line up with the magnetic field lines and point to the north and the south. And so that's how you can use a compass to know which way north is. One of the things that is very beneficial about that is the fact that our sun is constantly spewing out charged particles into outer space. It's not just sending out light and electromagnetic radiation, it's actually sending out charged particles. And those charged particles are being beamed in every direction, so some of them will be coming straight towards the Earth. Now, without our magnetic field, the beam of charged particles coming from the sun would strike into the Earth. But because of the Earth's magnetic field, what happens to a charged particle that goes through a magnetic field? It feels a force. And so most of those charged particles coming from the sun get deflected away from the Earth. And you can see that sort of over here. You can see charged particles coming in, interacting with the Earth's magnetic field and deflecting away. And that includes charged particles coming from the sun and other places in outer space. So the Earth is constantly being buffeted by charged particles in outer space, but our magnetic field deflects most of them away by that magnetic force. Again, remember, here's the takeaway. Anytime you have a charged particle passing through a magnetic field, that charged particle is going to feel a force. And this is how the Earth's magnetic field protects the Earth. Now we can contrast this with another planet in our solar system, Mars. Mars, unlike the Earth, does not have a big magnetic field. And so Mars has a very, very thin atmosphere. Most of the atmosphere of Mars has been eroded away into outer space, because over millions and millions of years, those charged particles have come in and struck the atmosphere of Mars and just basically caused the atmosphere to bleed off into space. It's like worn it away like a river can smooth away a stone. The atmosphere of Mars has been worn off for the most part. There's still some there, but not nearly as much as it was in the distant past, and it certainly doesn't even compare to the Earth's atmosphere. That's because the Earth's atmosphere is protected by the magnetic field. Now, if you have a beam of particles, we know that when the beam of particles goes through that magnet, that it's going to feel a force. The same thing is going to happen to a current that's traveling through a wire, like an electrical wire. And so here you can see the dashed wire where the electrical wire originally was, and then you turn the current on, and as those charged particles pass through that wire and enter into this region where there's a magnetic field, there's a force. Now, the other thing that's being shown in this figure, and it's a pretty important idea here, if the force is up with the current going one direction, if you reverse the current so that the current is going in the other direction, the force will also be in the opposite direction. So here, the current's going to the right and the force is up. In the other part of the picture, the current is going to the left and the force is down. It's opposite when the current reverses itself. Here's a simple application of this principle. This is something called a galvanometer. And it looks kind of weird, but what this actually is, it's a meter. And so you guys have probably seen meters, old-timey meters in movies where there's a bunch of numbers and there's a needle and somebody turns a knob and the needle moves up a little bit, indicating that something has changed. Well, the galvanometer is the basic idea behind that kind of instrument. And so what you have is you have a current going in here and coming out there, and as it goes through, it passes through this coil. And this, you can see there's this needle that's actually attached to the coil. Now, as that current goes in, it passes through, I don't know if you can tell, this is a coil that's wrapped around this thing inside this magnetic field. And so the current, it comes in and it goes through this wire. And essentially what happens is charged particles, in this case the electrons moving down the wire, are passing through a magnetic field and they feel a force. The bigger the current, the more force they'll feel, and the more this needle will rotate and turn. Now, this is the way an old-timey meter works, and depending on how it's calibrated, you can take this idea of a galvanometer and use it to measure all kinds of different things. Traditionally, it was used to measure electrical potential, which you should remember has a unit of volts, and also electrical current, which has a unit of amps. And so, incidentally, when it's measuring potential, it's called a voltmeter. When it's measuring current, it's called an ammeter. But the galvanometer is the basic design, and it can be set up to measure volts or amps. It can also be set up to measure resistance and other kinds of electrical quantities. So it turns out to be very versatile. Now, nobody really uses meters like this. As I said, you might have seen them like in old movies and things like that. But nowadays, we use what are called solid-state devices, which they're a little bit beyond the scope of this course, but they use modern electronics to do the same sort of thing. So you can have a digital readout reading these things out directly rather than having a needle that has to physically turn. This same principle is the basic idea of how an electrical motor works. So, for example, in your vacuum cleaner, there's an electrical motor that runs the pump to suck the dirt out of your carpet. It works on this same basic principle. So let's look at what we have here. We've got a magnet here, a permanent magnet that's creating a magnetic field, and we have a loop, and that loop is hooked up to a battery. So you hook it up to the battery and you get a current traveling through the wire, and then it goes down here, and then it comes out the other end back to the battery. So you end up having a current passing through this loop, which is in a magnetic field. Currents passing through magnetic fields feel forces. And so this loop will tend to come up and turn. Now, it may be hard to see here, but right here, where this metal loop attaches to the battery, it's two D-shaped objects. And so let me try to draw that. I've got basically this guy here and this guy here, and there's a gap between them. And so you can see where this gold wire is attached to the outside of the D. So if I draw that here, I might have this gold wire here and this gold wire on the opposite side. And so as this guy is rotating, this guy comes down, it's going to pass over this gap and end up touching here. This guy's going to go up and it's going to be touching up there. And what that does is it actually reverses the current, because that's necessary for it to keep spinning. And I'm not going to go too much into detail about why that works, but basically it's a very clever thing. If you didn't have this split in the middle here, what would happen is this guy would feel a force until it just lined up with the magnetic field. But by reversing the direction of the current, by having this guy come over here and this guy come over there, so this guy might be the positive end and this guy might be the negative end of the battery. So here the current is on the positive side, and when it passes over the gap, now it's on the negative side. And so you're reversing the current by passing over these Ds, and that keeps the thing spinning continuously.